Good afternoon, good evening, good morning, depending on where you are getting us from. Welcome to the second lecture in the series of solar power engineering. Today we look at the introduction to meteorology and climatology. And we will deal with the first part of lecture 2, and then in the next series, we will look at the part 2 of the introduction to meteorology and climatology. When we look at meteorology, we are basically looking at the study of the phenomena of the atmosphere. This phenomena includes the dynamics, physics, and chemistry composition of the atmosphere. So this dynamics and probably thermodynamics of the atmosphere will usually affect human life that we have on Earth. Then there are various aspects of meteorology that can be looked at, which is the physical, synoptic, climatology, dynamic, aeronautical, maritime, hydro, agricultural, aerology, and medical meteorology. So climatology, which is one important aspect that will affect the prediction of solar production, or if we are talking about wind, also wind production. So climatology, or the science of climate, simply is a scientific study of the behavior of the atmosphere, which is weather and also patterns of weather over a long statistical time length. So what we are saying is climatology is studying weather over a very long statistical time length. So when we are talking about the statistical time length, this can either be a decade or a generation. So in terms of years, we are saying this can be 10 years or it can be 30 years. But then if we say it's weather over a long statistical time length, then we know that when we narrow down to weather, we are simply saying we study the day-to-day atmospheric conditions and their causes. So when we are talking about climate and weather, we look at parameters like temperature, precipitation, which is rainfall, we look at wind, we look at solar radiation, we look at pressure, cloudiness, and also visibility. So in other aspects, we can actually say that climate is what you expect, because this will be over a long period of time. And then weather is what you actually get. So if we are looking at a longer period, there is a particular aspect of temperature that we expect. But then when we are looking today, we have the actual temperature that we get. So the two aspects, the weather that we get now culminates into the climate over a longer period of time. So for example, if we look at this figure that we have, we can see that on the right, we have got the wind, humidity, dew point, pressure, visibility, and also it's giving us how sunny it is. Of course, this is for a place in Skellefteå, Sweden, the northern part, and there is a snow actually that's showing, and also you see that it's minus 21 degrees Celsius. But then if we look at another temperature, another aspect of weather for the same day on a particular day, say for instance Zambia, this is a different aspect. So we see that different places will have different weather and climatic patterns. Also, if we look at additional information, we can see the temperature there, which was minus 20 degrees on the 5th February 2018. We can see the low clouds. We can see the wind speed in knots, and we can also see the visibility, meaning someone is able to see to a distance of 22.9 kilometers. Then we move on. We look at the Earth and its atmosphere. So the Earth's atmosphere, which is a thin gaseous envelope, comprises most of nitrogen and oxygen. This is some of the things that we learned perhaps in junior secondary and also in primary schools for some education system. And also we have small amounts of other gases such as water vapor and carbon dioxide. So the warmth for planets in the gas system is provided by the sun. If we look at table 1.1, it gives us the different composition of the atmosphere. Of course, we see that 78.08 and 20.95 is basically nitrogen and oxygen. Then if we move further into the atmosphere, we see that there are a number of layers that make up the atmosphere. And in the order, we see that we have got the troposphere, stratosphere, mesosphere, thermosphere, and magnetosphere. And in between these spheres, we have got the tropopause, the stratopause, the mesopause, and the exopause. So this is a composition that is expected in the atmosphere. And if we look at the two diagrams, we see that if we look at pressure, we look at altitude, we look at the height, they are actually in different heights. As you go further, you see different spheres of the atmosphere. This is the famous symbolic picture of the sun, which was also presented in the first lecture with the source NASA. So at this point, we look at solar radiation and energy. Solar radiation and energy. The sun is the source of energy that reaches the Earth atmosphere. So this energy is in form of radiation and it's responsible for temperature changes on the Earth's surface. So the same radiation from the sun can be absorbed, reflected, or diffused by particles on the Earth. This property of objects and particles is called the albedo. The albedo is the ratio of radiation returning from a given surface compared to the amount that initially struck the surface. This part was briefly covered in the first lecture, but if we go further on, we can see that fresh snow has got a very albedo between 75 to 95%. We have got also ice having a slightly higher albedo. So these are the things that we actually have on the Earth's surface and will determine how much of the radiation will actually be reflected, absorbed, or transferred by an object. Also, we can see that for Venus, Mars, the Moon, and Earth and atmosphere, we have 30 for the Earth and atmosphere, for Mars 17, for the Moon 7, and for Venus 78. And then when we come to solar production, solar radiation or irradiation, we have what is called the direct normal irradiation, DNI, and the diffuse horizontal irradiation, DHI. So the direct basically is solar radiation that travels in a straight line without any reflection nor refraction from the sun to the Earth's surface. Then the amount of radiation received by a surface that does not arrive on a direct path from the sun is what we call the diffuse horizontal irradiation. So DHI is basically scattered by molecules and particles in the atmosphere and comes equally from all different directions. Then we have got what is called the global horizontal irradiation, GHI. This is the summation of the DNI and also the diffuse in the normal. So if we use in terms of mathematics, we see that the GHI is actually the DHI plus the normal of the DNI. So if we use a graph, this is actually the illustration of the expression. So we see that the resolve of the direct normal radiation times cos gives us in the same plane as the diffuse radiation, which enables us to add these two components to come up with the global horizontal irradiation. So that's in a nutshell. Then when we come to irradiation, we also talked about the Boltzmann's constant in the previous lesson, which is governed by the energy is equals to the Boltzmann's constant times the rate times the temperature, surface temperature in the Kelvin. So if we push in the different parameters, we come up with what is called the solar constant, which is the energy received at the top of the atmosphere on a surface perpendicular to a beam. So this is 1367 watts per meter square. And in most cases, this is a value that we deal with when we start to do our calculation of how much watts is produced from a solar panel. So you find that different places on the globe will receive values around 1000 watts per square meter, either higher or a bit lower. But mostly in the lab, what is used is 1000 watts per meter square to actually parameterize a solar panel. So we see that the energy transfer from top of the atmosphere to the surface can actually be affected by the atmospheric composition, cloud cover, latitude, land, sea effects, difference in elevation, air temperature variation with time. So this is why you see that if we take, for instance, today at this same time at different places across the globe, we'll see that the irradiation that is being received is different. If it's during the day, then we see that the composition is different, the cloud cover is different, the latitude of different places will also be different. It's not the same. For those that are same, again, there might be some differences because of the air temperature variation. Then we need to measure this radiation for us to know that this is what is received at a particular place. We have the pyranometer and periometer, which are the instruments that are used to measure the irradiation that is being received at a particular place. So we can see the difference, the different types. The pyranometers, the first two, and the periometer, the other two, which measures the different aspects of irradiation. Also, if we take for a practical setup of a weather station to actually look at the irradiation, this is basically some of the things that we can actually find. Of course, with the improvements in technology, you find that these instruments are evolving, and also, but the architecture and the principle behind remains the same to measure either DHI, GHI, or DNI in terms of irradiation. And then to cap it all, getting from the report by the World Bank and also Solar GIS, we look at this resource map. So the resource map basically gives us the PV power potential. This is for Zambia. Of course, we can obtain different potential maps, resource maps for other places. So we see that it covers for a long period of time from 1994 to 2015. And it also gives us the daily totals and the yearly totals. So we are able to see in terms of different colors, with yellow being the lowest, and also dark, very thick purple being the highest. So even for Zambia, if we look at this map, we see that if we are able to install a panel in Kasama or a panel in Chipata and a panel in Mongo, at a particular time, the production will be different, which also attends to what we had actually looked at if we go backwards to say the transfer of energy is actually impacted or affected by the atmospheric condition, the cloud cover, the latitude, difference in elevation, and also the difference in the air temperatures. So if we look at what we have here, the resource map for Zambia, it actually explains, even for a country, you have differences. So from country to country, you expect such differences to be there. So the potential actually will be different from a country, and it's important to actually understand the resource map and also to use it when you're about to design or to recommend or propose something in terms of solar power production. So this is where the part 1 for lecture 2 ends. Thank you very much. You can subscribe, like, and share. If you have got comments in relation to this part 1 of the second lecture, you can actually send them to my email. Thank you very much, and see you in the second part of the second lecture.